All right, we're going to use Taylor's remainder theorem here to first estimate a function with a Taylor polynomial, and then use that Taylor polynomial to estimate a value for the function, and then thirdly, find an error bound for that estimation. So we're going to need this formula here to calculate the error bound. Remember, this remainder is going to be less than this expression here. And notice this remainder is a function of x. So if we use a Taylor polynomial and then use it to estimate some value when we plug in x, this expression here on the right will give me a bound on the error that we get when we use a Taylor polynomial. All right, here we have the function f of x equals the cube root of x. And this example wants us to find the first and second Taylor polynomials and evaluate it at near x equal 8. So we're going to do an expansion about a equals 8. So we'll find a Taylor polynomial, the first one and the second one. So that involves finding f prime and f double prime, and then evaluating those derivatives at 8. Okay. Of course, when I have f double prime, I'm going to have f double prime evaluated at 8 divided by 2 factorial as far as it's part of its expansion. Okay. Then once I have the Taylor polynomials for the first and second, so meaning P1 and P2, I'm going to use those estimates, that's an expansion about x equal 8, to estimate the cube root of 11. Now notice 11 is not 8. It's 3 units away from where we start expanding. That's okay. Okay, so here I've got a Taylor polynomial expanded about x equal 8. I'm going to use it to estimate when I move away from that. Okay, that's quite all right. Okay, so once we do that, we'll find an estimate of the cube root of 11 using our first and second polynomials, and then we'll find an error on those estimates. Okay, let's look at what the textbook does first. First, you're going to need to find some derivatives. Here's f of x, the cube root of x. F prime, right? This is x to the 1/3, so it's going to be 1/3 x to the minus 2/3. There it is. I have 1/3 x to the minus 2/3, and so differentiating that again, I have a minus 2/3 times 1/3, which would be minus 2/9. There it is. And then minus 2/3 minus 1 is going to be minus 5/3, and there's the x to the 5/3 and the denominator. Okay, so notice f at 8 is 2, f prime at 8, right? You put an 8 down here, the cube root of 8 is 2, 2 squared is 4, 4 times 3 is 12, that's where they get the 12. F double prime at 8, right? The cube root of 8 is 2, 2 to the 5th power is 32, and then I have a divided by 2 on the numerator, so I'm going to have 1/16, and then 9 times 16 is 144, so I'm going to have a minus 144. That's f double prime at 8. All right, so P1, there's my C0, it's just f at 8, plus f prime at 8 over 1 factorial times x minus 8 to the first power. Okay, f prime at 8 is 1/12. So the first polynomial is 2 plus 1/12 x minus 8. Notice the degree of that is 1. That's the first polynomial. The second polynomial, I'm just going to add one more term. There's f at 8. There's f prime at 8 times x minus 8. The extra term is f double prime at 8 over 2 factorial x minus 8 squared. F double prime at 8 was negative 1/44, and there's going to be a 2 factorial, which is 2, so I'm going to get minus 1 over 288 times x minus 8 squared. So here's the second Taylor polynomial. All right, so these are going to use to estimate f of x equals the cube root of x. That doesn't mean we just plug in 8 in all these. This means that we're going to estimate, well, maybe what is f at 9? What's f at 8.2? Right? These are polynomials whose input is x. All right, so we were asked to estimate the cube root of 11. By the way, here is 8, and so we're expanding about 8. P1 is a linear approximation. P2 is a quadratic approximation of the cube root of x. And this problem asks us, well, use it to estimate f at 11. So that'd be the cube root of 11. Notice here's 11, go up. It's going to hit my dark blue line here. And here I'm using the orange trace and the cyan trace to estimate the cube root of 11. So the cube root of 11, if I use P1, right, the definition of P1 now, remember, 2 plus 1/12 x minus 8. So P1 at 11 would be 11 minus 8. That's 3. 3/12 is 1/4. So it'd be 2 1/4. Right? If I P1, if I evaluate 11, I get 2 1/4. Using P2, here's P2 right here. Putting 11, right? That's the same thing we had before. That's going to be a 4, 2 1/4. Putting 11 here, we're going to get 3. 3 squared is 9. And then 9 over 2/88, and there's a subtraction there. And it looks like it's going to be negative 1/32 that I'm adding there. So negative 1/32. This is going to be 2 1/4, which is 2 8/32. So it's going to be 2 7/32. And that's what we get here, 2 7/32. Okay. So here's my estimate of the cube root of 11 using a linear approximation, 2.25. That's the first Taylor polynomial. And here's my estimation of the cube root of 11 using a second degree polynomial. That's the second Taylor polynomial. All right, so notice now we're going to go to finding the third part, which is, well, what's the maximum error in my first estimate and my second estimate? So now, notice, if I go back to the remainder theorem here, the bound on the remainder for whatever polynomial you're using is less than or equal to m, where m is the maximum of the n plus 1 derivative. And so really where it's all about finding that maximum value of the n plus 1 derivative. Here's the n plus 1 factorial, and here's x minus a to the n plus 1 power. So really it boils down to finding the maximum value of the n plus 1 derivative. So let's go back to our problem here. And here we're asked to find the remainder error for the first and second polynomial. Here's the first, here's the second. So the remainder for 11, right? This is the first Taylor polynomial we're going to use. So f double prime, notice I had to go to one more derivative than 1, so that's f double prime. At c, 2 factorial over 11 minus 8. That's the difference here is going to be 3, so that's going to be a 9. It's going to be a 4, or sorry, 2 down here. So we need to know what the maximum value that f double prime can take on. Okay, so f double prime, remember, is minus 2 over 9 x to the 5/3. And it's going to be over the interval from 8 to 11. Well, it's going to be maximum when the denominator is the smallest. Well, the denominator will be smallest at x equal 8. Okay, so at x equal 8, we'll plug this into f double prime. We get negative 144. Okay, so the absolute value of the remainder, when I have 11 as an x value, so the absolute value of 144, the negative is still just 1 over 144 positive. There's the 2 factorial, and 11 minus 8, that's 3 squared. So when I crunch this calculation, I get 0.03125. That means that our estimate of 2.25 is going to be within, 3.2 hundredths, or this value here. Go to here. Let's do this for using the second Taylor polynomial. But since I'm using the second Taylor polynomial, I need the third derivative. Here's 3 factorial. Here's 11 minus 8 cubed. This is still going to be a 3. It's just going to be 27 now. This is now going to be a 6 down below. So f triple prime, here it is, 10 over 27 times x to the 8/3 power. When is this the largest? Well, on the interval from 8 to 11, it's largest when the denominator is smallest, which will be at 8. So we need to plug in 8 into our third derivative. We get this value. So that goes here, divided by 3 factorial times 11 minus 8 cubed. And we just get this, looks like 65 ten-thousandths, or 0.0065. So that's the maximum error if you use the second estimate for our, or P2, to estimate the cube root of 11. So these remainders are actually very important because it tells you, the difficulty of the estimate that you want to use. You don't have to go to the 8th Taylor polynomial or the 10th Taylor polynomial if you only want to be within a certain amount of error. Notice if I take the P2, which is the quadratic estimate, I'm well within 100th of a unit, right? So depending on the level of error, you can choose a certain nth polynomial.